Welcome everybody. It's my great pleasure to welcome you all to this online conference that is being organized by the Deputy Prime Minister of the Slovak Republic, Štefan Holý. I'd like to take a moment to introduce and welcome State Councillor of the Deputy Prime Minister of the Slovak Republic, Martin Fischera.
Hello, good afternoon.
Good afternoon, Martin, and it's my great pleasure to welcome the main speaker of today's session on the topic of digitalization of construction proceedings and urban planning, Professor Martin Fischera, who is the director of the Center for Integrated Facility Engineering and as well as the professor of Civil and Environmental Engineering at Stanford University. Welcome, Professor Fischera.
Great to be here. Thank you.
Thank you very much. And at the same time, I would like to extend my great and warm welcome to you, to the audience. Thank you very much for joining us. And without any further delay from my side, I would like to kick off this event, and I sincerely hope that you'll find this conference insightful, productive, and worth investing your time. And now I'll hand over to Martin Fischera.
Thank you, Daniela. So before I will hand over the speech to Mr. Professor, I would like to inform you roughly about the stage gate process of the legislation. So in early October or mid-October, we've passed the Hospodárska rada vlády and the legislation Rada vlády. And since then, we are waiting to be admitted to the government. The good news is that we will pass that on Friday this week. And hopefully, because as you can imagine that we've done a lot of work to succeed, so we have a good hope to went through the government and proceed to the parliament early February next year. Both elements, of course, indeed urban planning and construction law as such are ready to be passed through, and also creation of the central unity as well. So part of the digital solutions which we are about to submit together with the law are the biggest question mark, and on the other hand as well the challenge. And because we are aware of all these facts, we get in touch with Stanford University to proceed further with the discussion and create even the proof of concept of the ideas the law is just about to establish. And with this, I'm handing over the speech to Mr. Professor Fischera. Thank you very much.
Great. Thank you so much for inviting me, and it has been fun already and stimulating to work with you for the last few months. To envision how a fully digital built environment for Slovakia could work, how we could create it, and what we could achieve with it. And I want to give you some background on the work we're doing at Stanford and the context. So you have an understanding of this basis foundation for our collaboration. And then hopefully together we can envision how we can create this digital built environment for Slovakia and the ecosystem that will result from it, and use it. To give you just a little bit introduction to myself, so you know where I'm coming from. I'm coming from this yellow house there, which is in a small village called Tägerwilen, which is right at the border to Germany, in northern Switzerland, where you can see the buildings in the background. It's already Konstanz in Germany. And to the left, you see my father crouching down. He worked in construction, so I grew up around building things all my life. And as we were building our house, I was 11 years old, and as every client, we had more wishes than we had money. So we children, my younger sister and I, had to help on the weekends and do various tasks on the house. So my father asked me to do this work on this one weekend on the upper floor, and so I did the job. And then I said, "Dad, I'm done." So he came and looked at it, and he said, "Yeah, it's okay, Martin, but you know, if you had used this particular tool, you would have done a better job." I said, "Yeah, I know." Then he's puzzled and looks at me like, "Well, why didn't you use it?" And then I said, well, the tool was in the basement, you know, and I would have had to go down 2 floors and up with it. Yeah, I'll just do the job without it. That seemed too much trouble. And to that, my father told me these words. You are an idiot if you're not using the best tool possible. So now you know where I'm coming from physically, but also in my mind, because this has stuck with me. I'm always looking for the best tool, thinking, are we using the best tool? And of course, in the last few years, what is the best tool has really changed. And I think this is creating the need for, but also opportunity, the legislation and the vision we have of a much more efficient, digitally enabled built environment for Slovakia. And I think eventually beyond, because I'm convinced this will open up other opportunities beyond Slovakia for people in Slovakia. So that you know what I'm doing at Stanford, I have been teaching there for 30 years on the faculty side. And right now I'm teaching a little bit too many classes, but I find them all exciting. So, but you can see they are related really around many of the advanced topics like robotics and AI, industrialized construction, to bring emerging methods to the next generation of people that are involved with building clients, agencies, and of course various companies, technology and otherwise. And the SciFi that Daniela mentioned at the beginning is the main research center in this area at Stanford that I direct. And it's a collaboration between industry, when I say industry, meaning really everybody that has something to do with creating buildings, and us on the academic side. And the goal is, in this community, to invent the next practice for how we create the built environment. And this applies to all the phases and to all kinds of structures, which we're showing here. So this is for individual buildings or plants or infrastructure, and at various scales and for all the phases. Because we have to simply improve, it's simply too costly today to create, maintain, update this built environment, the infrastructure and the buildings. So we need to create higher productivity, reliability, innovation, sustainability. That's what we want to achieve together. These are our industry partners at the moment. Some you recognize. Actually, I just saw a car from Hilti drive down the street the other day, just 10 minutes ago. So some of these companies you probably recognize here. Well, of course, Google as a building owner is very active with us. McKinsey on the consulting side, a globally known company. Bouygues, I think, quite known in Europe from France. So we have building clients. We have government agencies like the General Services Administration from the US, and engineering construction companies, as well as technology providers like Autodesk or Trimble, that together help us create the next version of how we design, build, and operate buildings. And so on the basis of these many examples, what's exciting for us in this collaboration is that we can do more proof of concepts, illustrations of how we might work in the future. But what is different here is that we can connect them with a common information basis that connect buildings, infrastructure, natural built environment, which is what creates a lot of the friction and inefficiencies in today's ways of making the built environment. Because we have to get better at creating our built environment. Because globally, we just see a huge demand for more infrastructure, more buildings, because the more infrastructural buildings we have, the higher the GDP, as you can see from the graph on the right. Maybe we can afford more infrastructure, or the larger infrastructure allows us to make a higher GDP. I'm not totally sure which way the direction, probably both are true. And as we look at the world where the lights are not so bright, tends to be the places where they're on the left side of the diagram on the right, where there is a lower GDP and lower infrastructure. So they want to achieve our GDP. So we will see, as the world tries to get richer, more construction. But I don't think we can afford to do the construction the way we have been doing it economically, environmentally, and socially. So we have to find dramatically better ways of creating the built environment, which is what we can do at scale here in Slovakia, thanks to the law that's put in place that enables a massively digital representation of the built environment, and then further use, creation of the physical and digital built environment. Because we have many, many emerging technologies, as you know from the news every day. We hear about mobile technologies, cloud technologies, GPS, laser scanning, and sort of technologies that connect the digital and physical, machine learning, AI, robotics, additive manufacturing or 3D printing, Internet of Things, virtual reality, augmented reality. Any one of those technologies actually already opens up a lot of new opportunities. The reality is that they are rapidly developing as we speak. Just last night, I had an interview with one of my colleagues at Stanford working on virtual reality. I thought I knew something about virtual reality because I'd worked with it quite a while, for over 20 years. But hearing from a researcher that develops virtual reality was really eye-opening in terms of basically saying, you know, in the future, basically, virtual reality, augmented reality will just be with us. It's like we will be wearing it. So you won't really need a cell phone anymore. It's, you know, we will be much more embedded in the physical and digital environment simultaneously. So that's what they're working on. And so we have a need, but also opportunity to leverage these methods and technologies for our work in related to buildings and infrastructure. So we need to envision that, but typically around the world I find surprisingly limited vision for how the built environment could evolve with all of our contributions. And that's what made me so excited when I got contacted by your ambassador to the US, asking me whether I would explore a research collaboration with Slovakia under the leadership of Deputy Prime Minister Stefan Holy. Because I saw, finally, I was very excited, a vision for how we can leverage all of these technologies for the benefit of us working in construction, understood very broadly, in the service of society. So why could this be important, and what could, what benefits could we get? I want to illustrate that with a couple of case studies we did to understand the opportunity from digitalization. A few years ago, we studied how engineers in a major engineering company, globally competitive engineering company, how they're working, where are they spending their time? And we found that indeed they spend actually 38% of their time doing engineering. We were actually a bit surprised. We thought that they are engineers, that they would be maybe spending 80% of the time engineering. But we found they're only spending about 38% of the time engineering. So what else are they doing? We also found that 8% of the time they spend planning. Okay, that makes sense. The rest of the time, the 54% of the time, they spend managing information, finding the right information, organizing the information, sharing the information, etc. Because without information, you can't do any engineering. And so this was a necessary evil that they had to deal with. And I think everybody in the company was really surprised by this result. They knew that they had to spend some time on the information side of things, but 1 in 2, or even more than 1 in 2 engineers doing only that was a really eye-opener for this organization. And it really highlighted the opportunity that exists from creating digital information that is shareable and accessible. It's difficult today because, of course, we need to bring together for any project many specialists, and they need to be, of course, efficient in their specialty, and so they working in these silos. And then, but on any project, we have to bring information from all of these silos together, and that is just really painful, at least in my experience. It doesn't matter whether the project is in Lima, Peru, or in Zurich, in Stockholm, Palo Alto. The challenges are very much the same. But of course, with digitalization, we have an opportunity, if we set it up well, to dramatically reduce this effort of having the right information. Because as you know, right, if you don't have good data, you cannot have a consistent process, and you cannot produce consistently good results. But of course, we all care about good results, good outcomes, success. But if you go backwards, right, for that you need a repeatable process, a good repeatable process, and that you can only have if you have good data. I know this is a painfully obvious statement, no data, no process, no results. But if it was that obvious, we would see much better data and much better processes because everybody cares about the results. So it's a bit of a mystery to me why we haven't been paying more attention to it. And that was sort of, again, when I got a call from your ambassador, whether I would be interested in working together. I remembered sort of this statement I put together a while back. I said, yeah, we can finally get rid of this. Another study we did is, this was internal to a construction company, but I think this would be similar to many organizations, where we studied what would the effect be if digital information was available for every step. And we found that on average, they could save 85% of the effort. So they spend even more time than the 54% looking for the right information for every task. So this is, I think, a huge opportunity to do more things. Because one thing that people always tell me, Martin, yeah, you with your ideas, that we should do much more, we should do things faster, etc. We are already busy today. Well, yeah, of course we're busy today because we are spending, what is that, 7 out of 8 hours dealing with information, like at least in this company. I don't know what the numbers are in your company. It would be interesting to learn what you find if you did studies like this. Yeah, of course we don't have time to do more things. But if we had a digitally enabled process, I think we would find that we will have time, and I will share a couple examples. Because we have to work together on any good-sized project, we have to share information with each other. And we could see on this hospital project where we could track, we could find out who shares information with whom. So these are some of the main parties that worked on this hospital and who they shared information with. Each cell shows who shared information how often. The darker the cell, the more frequent that information exchange, the digital information exchange. And when we showed this picture to the project manager, he said, oh, yeah, now I understand why we had trouble with certain parts of the project. Because those were the areas where the cells are light blue or white, meaning very little information was shared between different parties, and then the parties were on were focused on different things, not really coming together. And being able to have a solid information basis for everybody on a project, I think will open up a potential that we can't quite imagine yet. At least that's, from the case studies we've seen, I think that's fair to say. Because when you don't share information in a timely manner, you introduce latency, waiting, which slows down the project, slows down the exploration of alternatives, makes it so that you're slow to market, makes it so that you make changes because now a new technology has appeared or the situation has changed, which then further increases latency and waiting. It's sort of this ongoing challenge of creating the right project and then doing so inefficiently. So we can leave that future behind by the foundation that is being laid here with the legislation. A critical technology to help us achieve a vision of a digital built environment is building information modeling, or BIM, because it represents the product, the things that we are building, maintaining, using. And without a digital representation of the product, we can't really do very much efficiently. And BIM is the first technology in the history, thousands of years of history of construction, that allows us to connect the visualization of our projects and the built environment with the data we need to engineer and manage it. And that is important because each of us have a role on projects to play, and to coordinate those the information that we all create and use when we are working in our silos is extremely difficult. That's where the 84%, the 50%, 54% of the time goes. So with BIM, we can simplify that so that we can see what everybody's thinking of and connect those visions, but also so that we can, for example, build the right quality the first time. So here you see an example where Max Bögel, a German contractor, connected the BIM with the specifications in support of the inspectors so that they could make sure that every single thing on the project was taken care of right the first time, and they would know it. This seems like a crazy big task, but once they set up the system, was actually less time in terms of inspecting, reporting, documenting, and moving the project forward than the old way. Or we can even automate certain tasks. Here, the design of a mechanical system in a plant, where basically the engineer says, okay, I need this amount of electricity and water and so on here, and it's come from there. Design a system, conflict-free, right? No need to go back and forth again and again. Oh, I put my thing here, I put my thing there. No, the computer can take care of these things. So that frees up our capacity for things that we are actually good at, instead of sort of this basic tasks. So BIM is really the foundation for this way of working. And over the history of SciFi, we have had many first applications of BIM for many types of projects around the world. I realize it's too long a list, and I'm not going to go through the list. I just want to basically highlight that we are working with our partners in industry to push the envelope in terms of how we use technology to integrate and automate the work of the many disciplines needed. Currently, what are the main areas of research that we're doing at SciFi? I put them into three areas: optimization, feedback loop, and management. What I mean by optimization is basically if we put yourself today and you say you need to decide what to do tomorrow, that could be literally tomorrow or in 10 years. Every day we make these kinds of decisions. And how do we know that we make a good decision? How do we make a good decisions? I believe that I've seen when we create more scenarios and we can analyze them more fully, we have a better chance of creating the best decision for what we should do in the future. And that we can only do when we have a sound digital basis and let the computer run optimization simulations and then present them to us. And then as a group, we can decide, yeah, we like this or we prefer that. So that's how I see people and these digital tools work together. And I will give one example just shortly. Feedback loops is using the digital methods to look into the past. That could be yesterday, that could be the last 10 years, on a project or across many projects, to learn what actually happened, to not only build on our own experiences, of course, we will have that, to combine those experiences with what we can learn from the analysis. And I will show an example and I'll talk about some others in the industry area, in the energy sector. And then management simply means developing the management methods so that we can manage the digital and physical environment. So let me very quickly illustrate these three areas of work. We have many projects in these areas, so this is just one example. On the optimization side, we recently completed a project with a property developer, architect, structural engineer, construction companies, fabrication companies, to fully optimize the steel structure for a office building. This happened to be in downtown San Diego. This was really not possible to date. You could optimize only for example, the criterion of minimizing the weight. But when you minimize the weight of a structure, then you end up with many different sections, steel sections, which you have to then connect in different ways with each other. So you end up with many, many different types of connections. And so then you spend the money you save on the material on the connections. So the idea is to figure out where is this boundary? What is the right trade-off between number of types of connections and the weight of the structure? And for that, we need access to the data from these different stakeholders and a computational environment that can automatically carry out the design. So what was the effect in a case study we were able to do? We were able to show that they could save about 10% of the cost of the structure. And you can see here, I'm not going to go through the detail here, but basically it was by understanding, we could achieve this saving by understanding this trade-off between material and labor cost. And I think that same opportunity exists in many, many sectors. We saw actually a similar example in renewable, in a wind farm development in Texas, where we also were able to simulate many, many different options, trading off the wind income from the placement of the towers with the construction cost of those towers. And by being able to optimize that, we were able to show that they could create the same amount of electricity with 8% less investment and 10% less land use. That was the particular case. Other cases might be different, but showing quite a nice potential when we combine what people are good at and what the computer can give us. The other thing is that these results are achieved in about an hour instead of weeks that we find typically on a project. So you can start to imagine then a very, very different development process that is either much faster or gives us many more options, or a little bit of both. And I think this is not just for steel structures or the location of wind towers. I think we can imagine this kind of method being used for really anything we design. In terms of feedback loop, I have an example here from construction, but we've also looked at many other analysis of historic performance. The problem here is for a company that builds a structure is every day to order the right number of parts. When they order too many, then they have to pay for overtime. When they order too few, then they're wasting capacity. As you can see here from these numbers, if you're a few hours off each day, very quickly this adds up. And this is a very good company. The case study was a large parking structure near San Jose Airport in California. Very, very good company, but still every day they were a few hours off. And over a few months of the project, this adds up. Money we don't have for other things. So by putting a IoT device on the crane hook, we could understand everything the crane is doing. And so we could really understand how the project is unfolding. But that required we had to create a new method to manage the project, because they're not used to getting thousands and thousands of data points every day. And so we were wondering, can we actually manage the project better with this much greater level of information? So for that, we were able to compare the cost of doing the work by, from day to day, comparing the today mostly analog methods with the digital method. And so here we can see that sort of the closer you are to horizontal, the black line in the middle, the lower your cost. And and you can see the darker, the gray circles are basically the cost with the current methods, and they tend to be farther away from the horizontal, from the line where you would be perfect. And the the colored circles are two ways of using the digital information, and they tend to be closer to the line. So showing that we have a better prediction and can use our resources more efficiently. So in summary, we were able to again reduce the time for this work from 2 hours to creating a schedule from 2 hours to 1 minute each day, and we were able to improve the prediction by 50%, making 50% fewer mistakes in terms of saying what work to do tomorrow. So in terms of managing all of this information, I'm thinking of I like this analogy of different levels of intelligence that we can see pretty well explained, I think, with when we think about maps and how we get from one place to the other. Some of you may remember the old times when we had to get a paper map and then we had to find where we need to go and etc. It was a lot of work to figure out how do I get from one point to the other. Today, of course, we simply put in information in the smartphone and then it tells us where we need to go. We can understand the road network. We can understand what's going on, why there might be traffic, or why it might be congested in some area. We can predict how long it will take if we leave now or in 2 hours. And in the future, we might even be able to drive there, in an autonomous car that just takes care of it. I think that'll take a while for the built environment to happen at this level, although in the energy system, this could happen, I think, at some point. But we need to decide as humans, what do we expect from the digital environment? Simply a description, an explanation, or prediction. And then manage that information to support that. So I'm excited here that we can work with a group of people that has a vision for a digital built environment so that we can actually have data that leads to consistent process and results by integrating the data, automating what we can automate, and then all benefit from it. So I look forward to creating this with you on the basis of your work, your new legal structure, and our work and network at Stanford.
So, yeah, go on.
I just wanted to thank you for your presentation. And I would like to as well encourage all of you to submit your questions, thoughts, or comments in Slido, either in English or in Slovak. There is just one very technical question that if those slides that you walked us through will be shared with the audience afterwards.
Could be.
Yeah, if you like.
Okay.
No problem. From my side. Yeah.
So just, as we said that we're going to take all the questions, so I just wanted to as well refer to this one.
Yeah.
Until we wait for the audience to ask any questions or observation. Martin?
Yeah, of course, I'm fully aware that we are overwhelming the industry to which we are just talking now, and of course it's always very specific to speak about very broad topics and then talk to a specific industry and find some overlapping with the theme. But anyway. We are quite sure that while the digital world is working in silos and working fairly properly for the companies like operators, telecom operators or energy companies, there was never an intention, either by government or by other institutions, to put all these different slides and layers together. And maybe we can somewhat elaborate a little bit what could be the benefit, let's say, in terms of real applications and usage of them in a foreseeable future, once we will achieve that common data platform.
Yeah. Broadly speaking, what I've seen emerge in the last few years is really, for the first time, at least in my experience, I don't know what your experience is, simultaneous understanding of demand and supply. These tend to be very fragmented, and we tend to have people focus on the demand, making assumptions about supply, and the other way around. And we were able to, especially in the provision of electricity and also some other energy sources or energy uses. See what can be done when we understand both of them simultaneously. We have had quite a few projects with our utility in our area, in where Stanford is, PG&E, Pacific Gas and Electric. They haven't been in the news in a very favorable light with the wildfires they have caused. Well, that's a different topic, but also important actually. We could also talk about that one. But we were able to, once smart meter data became available a few years ago, to understand how are their customers actually using electricity. And maybe you have done this analysis on the electricity side or the telecom side. What is really the demand? Because the assumptions they make, because they have to make assumptions on the demand, because they have to organize the supply. And the better they can match demand and supply, typically the greener, the more economic the production of the electricity. So we were interested in finding the right pattern of the patterns that explain electricity use, because it's not really feasible yet to predict for every customer tomorrow what are they going to need and therefore how will it provide it. But when we understand the patterns of use and how frequent a particular pattern is, then it becomes quite feasible of predicting the demand more accurately. And what we found is that, well, the utility had assumed that everybody was using electricity with a small peak in the morning and a big peak in the afternoon. But that proved to be not the case when we looked at the data. What we found is that only 14% of the customers actually used electricity in that pattern. And we needed to look at 109. We found that there is another 199 roughly patterns that explain electricity use by consumers in California. So we had, the basis of that was 66 million consumption days. So the good thing is there wasn't 66 million patterns, but there was also not one. So there was 200 patterns we found. And that was usually important in terms of understanding how to organize the supply, how to create incentives for customers to maybe change their behavior, because once you saw the patterns you liked or didn't like, and also the variability in the patterns, how could you get customers to sort of, that you don't like in terms of their performance, how could you get them to a use that was more beneficial, and also to see the opportunities for energy efficiency, and again target the marketing for energy efficiency more carefully to the right customers. So this was a project is ongoing, but we were able to show that thanks to digitalization, we could create these insights. And I see us sort of doing the same, but then actually much more here in Slovakia. And I think this connects also the telecom and the electricity side of things.
Before we take the questions, Professor Fischer, I just got the information that your colleague from US managed to
see him
join
clearly.
Oh, there.
Okay. That's
Okay.
good.
Hey, Ram.
That's perfect.
So my colleague normally sits in the office directly next to me when we are in the building at Stanford. But I think he's still at home since it's extremely early. So actually the work I was just describing is really, I don't know how much you caught that, Ram. I was just sort of describing how we analyzed data from PG&E to understand use patterns, to better align supply and demand, to identify the right customers for energy efficiency retrofits. But I think it might be nice if you want to share some examples of your work that shows the potential when we have really accessible, trustworthy information about the digital environment at scale. I mean, the built environment at scale.
I saw from your presentation, so it was great. I think you kind of summarized some of the major insights of using data. You had asked me to share 2 or 3 examples. So if I could share some slides, I can just show some pictures for people if they can see it from where you are. Oh, it's not allowing me to screen share.
Yeah, let's hope we will overcome some technical difficulties, but before you will get that access, Ram, if you could, maybe we are faster than I thought.
But say just a couple words about yourself too.
Yeah, I'm a faculty in civil and environmental engineering, neighbor of Martin, and I think I worked with Martin since day one at Stanford. We have collaborated for a long time on kind of understanding the energy consumption in the built environment from new types of data. And one of the key drivers and motivations to do that is that there are a lot of rules of thumb on how we think about energy consumption and energy demand. And so, for example, there's this thought that residential consumers have a certain load shape, meaning they time their consumptions in a certain way during the day, consume a lot in the morning, consume a lot at night. But when we looked at the data, that was not the case. There were roughly 200 different patterns of consumption, and then those could be grouped into some 9 categories. There were insights about how...
Did you want to show those slides? To show them for a second, but then it went away again.
Okay, let me just show that here.
Yeah, sure. So, why not?
Yeah, that was the illustration.
Let's dive deep for a while.
Okay. So here's kind of a slide with this work where we process data initially of 150,000 customers. This was provided by our local utility after about a year and a half of negotiations and proving that Stanford can be super secure with your data. So I'm happy to say that we overcame all kinds of obstacles. And actually now we have about 1 million customers from the utility that are reporting data to us. And this panel just shows all the different varieties of load shape. In fact, for the state of California, the utility here, everyone thought every single household consumes this dual peak pattern: peak in the morning, doing breakfast, etc., go to work, and then a peak in the afternoon. But you can see there's nighttime consumption, there's single peak, and in fact, on this kind of dual peak, you only have 14% of all customer days of data. So this type of insight showed the rule of thumb we use for planning out here was not right. And it can only be uncovered by the fact we had data for a lot of customers over a lot of days and high resolution data. Kind of a similar work, but on a different issue, was out here, the utilities told our students that we don't know where the rooftop solar panels are located in the Bay Area. And, our students heard that and went off. And, a few months later, a couple of them came back to me, my own students, and said, look, we needed some cloud computing credits. And we have this idea of mapping all the solar panels in the Bay Area using satellite imagery. And in fact, they were able to create an algorithm to do the mapping for the whole United States. So we have the most granular and detailed map of the locations of all solar panels in the country. Now, why? And this is about 20% more than the best database that is collected in the United States, which is by the Department of Energy. It costs about $4 to $5 million a year to collect that data, versus our method, was just running machine learning over billions of satellite image panels. Now, why is this important? So here's kind of why is it important. Let's just focus on this panel in the middle. It's just showing the number of systems per 1,000 households. And you can see here, as expected, that increases with income. But what is not expected is that it saturates after a certain level. And what this means is that we were able to build a model that predicts who will adopt solar panels and where that adoption will happen, which is several orders of magnitude better than what existed. Another example was that we created algorithms to kind of use Google Street View images, as you can see here, looking up in the upward view of Google Street View, and map all of this distribution infrastructure. Surprisingly, all of this data is not public, and not only it's not public, but even for utilities, they don't have accurate GIS maps in many locations of the United States. So we are able to do that with this algorithm, including locating poles and the distance between trees and lines and things like that. But why was this useful? So once we had this map, we were actually able to correlate fire risks here in our area. We're having a lot of fires, as you have heard, caused by these distribution lines. And we were able to correlate fire risks with these lines. And we noticed a couple of important things. One, that on the right, in the left is your fire. On the right, you can see where solar was adopted. And we are seeing there is no real correlation between the two. If people were adopting a lot of solar where there is potential fire, that means there's less load on the grid, less risk of fire. That would be a good thing. There's no relationship there. The other thing we found out is that the undergrounding of lines is done with rules that are very reasonable, rules of thumb. You have to do it in high density areas where, maybe property values are higher also, so that they can cover for the cost. But as a result, what we have seen in California is most undergrounding is done at high income, low fire risk locations. And in fact, you would really like undergrounding to be done at high fire risk locations, which turn out to be also low income locations. So there is a difference in population exposure. There's also a difference in fire risk. And we were able to build an algorithm that says where ideally should you underground lines. You can do similar things for like predictive maintenance. So for example, you can use GIS data combined with the sensors that are deployed in the power network to predictively monitor and instantiate which locations should you go and do interventions, or maybe send a drone to map issues that are happening. So I'm not presenting slides on that, but I'll be happy to connect you guys with work that's happening on that area. We collaborate with a company called AutoGrid on that. And last but not least, I wanted to bring up this issue of EV charging. So we are trying to build tools out here to accelerate the deployments of charging stations. So right now, in California, it takes anywhere between 6 weeks to 6 months to kind of approve the electrical connections and the facilities of a charging location. And that has to do with the requirement that you need the electrical utility to approve it. You need the local city to approve it, and there's some coordination between the two. You also have a lot of requirements. So for example, one of the requirements is that the electric utility says there's only this much capacity that I have to approve for solar and for EV chargers. And one of the things that we wanted to do is to create a tool to calculate that capacity automatically, because we noticed the capacity was being calculated with out-of-date data. So it ignored the existing solar, it ignored the existing chargers. And in fact, what we did was two algorithms. One that mapped the chargers from construction permits. So we have chargers in homes and buildings and also public chargers, and then correlated those with all the solar locations from our solar mapping. And we showed that a lot of the charging was happening when the solar was on, therefore not really affecting the grid. So you can add a lot more chargers and a lot more solar. We are also building tools that would help kind of reduce this approval periods by automating the electrical evaluation of a site using very high resolution data-driven simulations, as well as this automated capacity calculation. I think this will be very, very important. I think recently we had several interesting conversations that today in the world, deploying these charging stations at high speed is a major issue nearly everywhere. I would say in the United States, it's certainly a big issue. I think in Europe, there's many countries where the deployment rates are very slow. Just as kind of some numbers, we had an event here, and Tesla, which is kind of the most famous electric vehicle company, said they have the desire to deploy 1 to 2 charging stations a week. But because of this whole delays and lags and so on, they're only able to achieve, maybe 1 to 2 charging stations every couple of months, which is really a huge, huge difference in speed. And I was just thinking, when you presented this kind of vision for integrated data, a complete GIS picture, we could create the most efficient and fastest deployment of a charging network in the world just in Slovakia. And I think that would be a real demonstration of the benefits of this. And I'm sure there will be several of these EV companies interested in actually paying and participating on something like this exercise. Beyond that, I also feel on the consumption side, on the demand side, having the kind of information that is being collected in Slovakia, which is all the details of the building in terms of infrastructure, and in addition, thermal imagery. This is kind of like a dream that, Martin had when I came in. Then I joined the dream, and we have been dreaming since, which is, wow, it will be amazing if there was a location where we knew all of this information, because we could just build a map of where is all the thermal leakage in the whole Bay Area. And this map would be shared with vendors and with many others to immediately offer a marketplace where folks can go in and bid on projects for energy efficiency improvements, and really save up this cost of identifying where the issues are. This is typically, the customer acquisition cost. And just so you have an idea, for example, for solar, which is considered a sort of energy efficiency improvement, but in general for energy efficiency improvements, but for solar, customer acquisition cost today corresponds to 30 to 40% of the total cost of a solar project. It's not the solar panels, it's not the hardware, it is customer acquisition cost, which includes marketing. Then about 10 to 20% is the permitting cost. So more than half the cost are these two, cost sources, which is incredible if you think about it. And you can get away with, get rid of all of that. I imagine similar numbers would show up if somebody did the calculation for energy efficiency in buildings. So those are three ideas that I feel very passionate about. One, this idea that maybe there is one place in the world where we can show how utilities and cities can work together with GIS data and deploy stations for charging much faster than everywhere else. The second one, and I think this is very, very powerful, can we create this sort of energy efficiency marketplace that is frictionless by automatically detecting all the locations where you have an opportunity to do this, and then facilitating for vendors and utilities to offer those services. I mean, that has to come from industry, but we could help by creating this map. And last but not least, of course, there is this dream in the electric, power sector of predictive maintenance, which is trying to get ahead of failures and faults predictively from data. I think this is possible to some extent. It's super exciting, but I think to be able to do that, you need more than the data that just sits at the utility. You need to know the state of other infrastructure from GIS and need to combine all these sources with really clever algorithms. So lots of opportunities to be world first, just because you have this unique vision, which I think is fantastic. And I think, the fact that you guys found Martin is also fantastic, because he has been thinking about this since I've been at Stanford. That's 2011. So 10 years in the making in some ways to find a place where this could be done. So this is great.
Thanks, Ram. There's actually a question whether, it says, you've shown various attractive use cases for advanced algorithms. Are any of them already publicly available?
Yeah, we publish all our code in open source, as well as many of the results when they're allowed by the vendors of some data, for example. So we have a package called Wisdom that helps you analyze all the smart meter data and find patterns and so on. It can be downloaded and utilized. It's actually utilized by about 12 utilities in the US regularly today. There's many more that have tried it and so on. Deep Solar is also a publicly available algorithm. You can go to deepsolar.stanford.edu, look at the results in the United States, and download all the code for doing the deep learning and run it. So, yeah.
And then there is a question. Do shared databases have an error correction process in place if someone enters incorrect or imprecise data? Do we have experience with that?
Oh, that's an excellent question. We provide the data that we mapped, and you can create those facilities. As a university, it's hard for us to manage that, but in terms of showing the value of this type of mapping to correcting errors, we just published a paper where we show that in Germany there is a public registry of all solar panels. And we were able to go into this public registry, and using our method, we corrected about 20% of the entries automatically, showing there were a lot of mistaken locations, misreported GPS, and they don't have GPS locations. There's inexistent panels being reported. So we were able to clean that up just using these algorithms. So there is a lot of potential for that, for sure. And same for the GIS project for the distribution lines. We also obtained GIS data from the utility, but we were able to use our algorithm to correct some of those maps and also identify overhead and underground lines, which are not indicated in the public data from the utility.
I will just step very briefly into this, the so-called rule of thumb and total cost of ownership. That's a kind of a common denominator of all of these things, and that's the data as such. So without data, we are all running blind, and actually the whole project we are just about to start is about to acquiring the data in a good quality on a timely basis. What is important to say is, of course, the inaccurate data, so-called garbage in, garbage out. Of course, that's a part of the liability. So if someone holds the infrastructure and doesn't reveal the location, does not necessarily mean to everybody, but to certain authorities, then that has something to do with the liability as well. And if there is a good motivator to reveal these data also for further processes and even other businesses, that would be a very good motivation to keep the data right on a spot.
It's an excellent observation. Completely agree with that.
Let's see, there's a question around, are we just doing buildings or also infrastructure at the national scale? So I think this was, probably written before Ram presented. So between various colleagues, we are definitely working at many scales. From actually some of my colleagues focusing on the performance of just the materials in the context of structure, in the context of a building, in the context of a network, and then others taking a country level view of infrastructure. So we definitely have work in all of these areas. What sets of data do we, at the national level, do we consider as particularly essential to minimize silos? Any thoughts on that, Ram?
I would say all of the above.
Yeah, exactly.
As much data as you can. I think GIS information is, of course, super important. Other types of measurements for buildings, for example, I think thermal measurements of buildings will be very valuable. Information on, HVAC types and things like that, or satellite information, which helps you actually detect and map those. We can also say the consumption of the building is very important. And having access to that information would allow us to really create rankings and efficient frontiers to show, I think, a building comparable to yours that's efficient, and that will allow you to understand what's the differences. So, and as you can see, we can build up on this story and add more and more layers. So the more data, the better. But I think it's data beyond GIS combined with GIS is what makes it super powerful.
Yeah, no, that exactly what I've run into a lot in my work is that people want insights. And for that, you need a lot of data from different parts of your business that are connected. And the people that have connected data don't have a lot of data, and the people that have a lot of data don't have it connected. At least that's what I find. And as a result, the insights we can generate are still somewhat limited. And and then we are back to just anecdotes. And those anecdotes we've seen again and again. Actually, what we believe is not actually always the case, or actually surprisingly rarely the case.
Yeah. I would say one belief I used to have was, companies are fairly efficient. Therefore, if a company themselves contained all the data, they should be able to do a lot. But these silos can be formed even inside a business. It's not just with respect to data that you may not have. It might be with respect to data that you have, but you're unable to share within your organization. So even there's a big issue. But once you find the benefit, once you can show what you can do with it, then suddenly all of those silos can be broken down very quickly.
I would say that, thank you very much, Ram. I would say that the last question will be here from Mr. Brčák, I guess, and then we will end up the session. So maybe that's more for you, but I can step into that as well.
Yeah, what's your take on 3D scanning of buildings at scale? Do you consider it as a promising approach, or rather not mature enough for civil engineering use cases? I've about 20 years of experience with laser scanning at buildings. And I think we have yet to do a laser scan where it didn't pay for itself. Because at least in the US, the documentation of the as-built condition, we have not found a single building where the documentation that existed actually matched the reality. And so the planning errors that happen when you just proceed on the documentation you have dwarfed, the cost it would have taken to laser scan. So and the scanning costs have gone down dramatically, and the ability to manage scans has also gone up significantly over the last 20 years. So in my assessment, it is absolutely feasible to do it at scale, or certainly in the foreseeable future.
So one of the aspects or thoughts regarding the law we wanted to introduce is that we will, at the end of the all processes, we will introduce also so-called final check, or better to say the comparison in between as built and what has been provided. So and that will be the correction factor for at least new buildings. And the 3D scanning, of course, if there will be a motivation in some of the applications which might come up and pop up in the next foreseeable future, then the 3D scanning will be very, of course, very attractive. And there are technologies, at least we saw also some of them during our visits. So technology, I would say, is really catching up very quickly. So it's possible.
If you have one more minute,
sure.
I'm just reminded of an example from one of our collaborators from ExxonMobil. He takes satellite data, and they have very big projects, and he looks at the progress of their project just month by month. And he has now looked at many projects, and he's able then and can relate it to this project was successful, this project was late, this was not successful, and so on. And then he did this analysis on this one project in Texas, and he calls the project manager and says, "You're in trouble, aren't you? It hadn't reported it to the company that the project was, maybe running a little late and over budget." And the project manager goes, "How do you know? You haven't even ever been here." He says, "Well, bit scanning. So maybe you think this is a little bit scary, but I think in terms of managing, using, at the end of the day, we have, like we had in our building at home, we have more wishes of things we want to do than we have budget. And that's the case everywhere. So at the end of the day, we have to find the best use of our resources. And whatever means that's kind of where I'm coming from. Whatever means we can use to do so, let's do it.
I can still see that there is something popping out on the chat, but I can't really see it from a distance. If it is a question or if it is something that we have already answered.
I just posted a comment that for the power sector, 3D scanning can be a groundbreaking technology. Mm-hmm. I think, in accelerating and automating power interconnections, in accelerating the approval of solar and EV deployments, and assessing building efficiency, intervention opportunities, and the potential costs. So this is something that is a revolution, and we have not used it. We are just scratching the surface today with LiDAR and trying to map vegetation, because we don't have, you need a lot of buildings scanned to say something about the power system. So this is really amazing. And when Martin told me about the project, I was like, yes, I definitely want to figure out how to use this information, because it can be a great resource. So no doubt to me that's the next part of the next generation of challenges in our sector.
Wonderful. Just there is still this question, but I think that we already taken it up here about the silos, so that's why. Yeah. So I can just give a sign, to our tech team that this has been covered. As I can't see any more questions, I would like to thank you very much, Professor Fischer, for joining us and for going through the whole presentation, especially your colleague Ram, that has joined at a pretty early morning hour, I would say, in the US, if I'm not mistaken. And as well as to everyone of you who have joined us today. And this is not the last session of such a kind that we are running, and hopefully there's going to be more sessions like this and more discussions like that. So this is just the start, as I would describe it. And I would just leave a couple of last words to the State Secretary, Mr. Martin Hipke.
So thank you very much one more time to Professor Fischer, and we hope that you will join forces together with us to get it done on the legislation side, and have your great support on the practical side. Thank you very much one more time, and see you at a later stage. Thank you.
Thank you very much. Bye.